A property that comes in handy when working with improper integrals is L'Hopital's rule. So here let's do a little review of L'Hopital's rule. So for L'Hopital's rule, we need to have a function f and g that are differentiable at x equal to a. And as your x's go to your a, your function f should go to 0 and your function g should go to 0, or your function f should go to infinity and your function g should go to infinity. If you have this scenario, when computing the limit as x goes to a of the quotient of f of x divided by g of x, you can apply L'Hopital's rule. And L'Hopital's rule would say that that's the same thing as the limit as x goes to a of the quotient of the derivatives of the functions. So let me give you some examples that highlight different uses of L'Hopital's rule. Here's an extra problem. Suppose we're trying to take the limit as x goes to 0 of cosine of x minus 1 divided by x. Try plugging in 0 to the top. Try plugging in 0 to the bottom. If you plug in 0 to the top, you'll have 1 minus 1. That gives you 0. If you try plugging in 0 to the bottom, you'll have a 0 there. This is what's called as indeterminate form. And really, it's sort of like a tug of war. The top wants to go to 0, and it wants it to make the fraction 0. The bottom wants to go to 0, and it's trying to make the fraction infinity. So here we can apply the L'Hopital rule computation and turn this limit into the limit as x goes to 0. The derivative of cosine x minus 1 is negative sign. And divide that by the derivative of x, which is just 1. So this limit doesn't have that issue of having that ambiguity of 0 over 0 anymore. If I plug in 0 to the top, I get 0. Plug in 0 to the bottom, there are no x's, so your answer is just 1 on the bottom. So ultimately your answer is 0 over 1 or just 0. So L'Hopital's rule allows us to deal with these cases where we have these ambiguous scenarios of 0 over 0. L'Hopital's rule also works when dealing with limits as x goes to infinity. So in this extra problem, consider us wanting to take the limit as x goes to infinity of 5x squared plus 2x minus 3 divided by 7x squared plus 1x minus 2. For the top, if I plug in large positive numbers, that's going to go off to infinity. For the bottom, if I plug in large positive numbers, that's also going to go to infinity. So I have an infinity over infinity indeterminate form. The top being infinity or going to infinity wants to take this whole fraction to infinity. The bottom going to infinity wants to take this whole fraction to 0. So we can apply L'Hopital's rule, and this becomes the limit as x goes to infinity of taking the derivative of my numerator. That gives me 10x plus 2. On the bottom, taking the derivative of that denominator, you have a 14x plus 1. Cool. Are we better off than where we were? Can we evaluate this expression at infinity? Well, again, if you try to plug in large positive numbers to the top, you're going to get infinity. If you try to plug in large positive numbers in the bottom, you're going to get infinity. So we have another indeterminate form. That's okay. it's allowed to use multiple iterations of L'Hopital's rule. And here we get the limit as x goes to infinity of the quotient. The derivative of 10x plus 2 is just going to be 10. The derivative of your 14x plus 1 is just 14. So your final answer is the limit of this constant is just going to be that constant. And if you simplify, that's 5/7. Moreover, sometimes the limits that you're working with are candidates for L'Hopital's rule in disguise. So in this extra problem, consider us wanting to take the limit as x goes to infinity of 3x plus 1 times e to the negative 2x. Well, first of all, this doesn't really look like a candidate for L'Hopital's rule because it doesn't look like a fraction, right? But we can make things easily look like a fraction by moving things around. In particular, that e to the negative 2x, we can kick it downstairs and make it look like 3x plus 1 divided by e to the positive 2x. Aha. So if you try to plug in large positive numbers to the top, that 3x plus 1 is going to go to infinity. If you try to plug in large positive numbers to the bottom, that e to the 2x will also go to infinity. You have an infinity over infinity indeterminate form, which is a candidate for L'Hopital's rule now. So then this converts into the limit as x goes to infinity of the derivative of 3x plus 1 is simply going to be 3. The derivative of e to the 2x is going to be e to the 2x with a 2 in the front. And now we don't have that issue of that ambiguity of infinity over infinity. The top is always going to be 3. And for the bottom, as you plug in large positive numbers, 2 times e to the 2x will blow up to infinity. So you're going to have 3 divided by a gigantic number. So this guy will go to 0.